Great, thanks, Dare. Very, very kind. So my association with Kentucky, beyond my good friend Dare, is twofold. So one, my late grandmother grew up in Paris, Kentucky. So I say, she grew up in Paris, and most people obviously think she's European, but you guys, right, would recognize that she was from here in Kentucky. And then the other is, growing up, my family had a yearling operation. I'm from Kansas originally. And we bought cattle out of Kentucky for a number of years. I'm not going to tell you what order buyer we used, because that's kind of like telling you, who I voted for. You say, oh, man, I can't believe you used that guy. But we certainly took a lot of cattle from your neck of the woods and brought them to Kansas. And like I said, did that several times, so that means they must have worked. So appreciate that. Question for you guys, how many of you sell bulls? Just so I get a sense, all right? I'd submit to you, you don't, right? I'd submit to you what you do is sell genetics. The bull is the vector of those genetics. So at UNL, I teach a class that puts on our annual bull sale. So we've got a seed stock herd, and we sell bulls that come from that herd in an annual production sale. And that's what I try to convince the students. We're going to sell genetics. Bulls are the vector that carry that genetics. And once you think that way, a lot of this, I think, becomes not only simpler, but really codifies how important it is, right, that you're really selling genetics. This is the basic model, phenotype. What we see comes about through environment and then also genetics. So the fact that I'm the optimum height for a middle-aged man, most of you are entirely too tall, is part genetics and part environment, right? We could break this down even more into additive. That's the A, that's part of genetics. The additive genetics is what we capture through EPDs. That's the part of genetics that is reliably and predictably transferred from one generation to the next. But we also have the D and the I. Those are both genetic effects too. D is dominance and I is epistasis. Epistasis is the interaction of genes at different spots in the genome. The dominance and epistatic bits are what your customers hopefully capture through a well-implemented crossbreeding program, right? And I'm a huge advocate of crossbreeding, but it's got to be with design. Plenty of people do crossbreeding with no thought, right? It needs to be a well-designed crossbreeding program. So what you do is increase the additive genetic merit. I want to put a little finer note on this, though. We could say that phenotype comes about through genetics, known sources of environment, that's the big E, and then the little e is air, right? That's the stuff that impacts the phenotype that we just don't know about. It's not captured through contemporary group effects or sex or age of the animal or the animal's genetics. It's something else that we just don't know. And so what I want to make sure is clear here is we think about a trait like fertility. Dare mentioned it's lowly heritable, and it certainly is. Oftentimes what people think is, well, genetics explains about 10% of the differences among animals for something like fertility, so that must mean everything I do as a rancher is the other 90%. That's not really true, because when we calculate those heritability estimates, we adjust the phenotype for all the known sources of environmental variation, and what's left over, genetics explains about 10% of. So the important thing is, if your customers say, I've got the repro thing covered through the way I manage them, I don't need to worry about trying to improve genetics there, they're wrong. Okay? They need to care about improving genetics for even lowly heritable traits. All right, so this is the test material here. I'll let you just take a few minutes and copy it all down. Here's what I wanted to explain. This is Dare mentioned Charles Henderson. These are the mixed model equations that we use to calculate EPDs. And what I want to try to convey to you is This complex statistical machinery that we uses the data that you send in. Oftentimes producers think, I do all this work on ranch or on farm collecting data, and you guys just basically draw numbers out of a hat to assign EPDs, right? That's not the way it works. It's the data you turn in that drives these complicated statistical equations, right? So the X's here really relate the environmental effects to the records. So what contemporary group did this animal fall into? What was this animal's sex? What was this animal's age? You misassign those things, and it happens. At UNL, we rely on student labor for our seed stock herd. It's frustrating at weaning time to find out that bull, right, wasn't a bull calf. It's amazing how we can get that wrong sometimes. I mean, it's right there, folks. But you've got to correctly assign those things. The Z's assign an animal to the record, right? Did I get the right weaning weight with the right calf? That K is kinship, right? Am I doing a good job recording pedigree? The Y's are the phenotypic data you turn in, the records. Am I doing a good job of collecting data? And that funny symbol that I call an alpha is related to heritability. And if we turn in messy data or we incorrectly assign animals to records, we impact that, right? So the machinery used to calculate EPDs is very much based on not only the amount of data you turn in, but the quality of data you turn in. And it all starts with contemporary grouping. A contemporary group consists of animals that are given an equal opportunity to perform, right? They start out with an equal chance. So we can identify fair competition, and it's formed by management information. So if I have a group of bulls, and one of them just looks really good, and I think, you know what, I'm going to pull that bull out, I'm going to feed him a little bit better because I want to put a halter on him and take him to some show. He's in a different contemporary group now. I gave him an advantage through the way I'm feeding him. So now he may be in a contemporary group of 1, which means he has no competition. The records you collect on him aren't going to impact his EPD. Right? So it's got to be a group of animals that were given a fair opportunity to perform. And that's really the basis for all of our genetic comparisons. If you have multi-breeds, right, so maybe you raise Red Angus and Gelbvieh, an example, right? If they are truly managed the same way, they should be in the same contemporary group. But if they're managed differently, then they should be in different contemporary groups. Right? These large multi-breed genetic evaluations like International Genetic Solutions that conducts the genetic evaluation for pretty much every breed except for the Indicus, Angus, and Hereford, right? They rely on contemporary groups that have a mixture of breeds in them because that's the only way they can really partition genetic differences within a breed from breed effects. So if they truly are managed the same, multi-breed should be in the same contemporary group, but don't force that case, right, if you manage them differently. I understand that particularly for some breeds, you pay for every record you turn in. Okay, some are inventory based, but some you pay for every record you turn in. So I understand the temptation to say, well, if it's not a good one, do I really have to pay the money to submit a record to the breed association? But you're shooting yourself in the foot if you don't do that. So what I have on your left here are adjusted weaning weights for 10 calves. And then I have the deviation of their record from the contemporary group average and use that to calculate a ratio, right? Dare talked about ratios. Now what if I just turned in or submitted to the breed organization the top 5 that were quote-unquote the best, the heaviest? What I show there is the contemporary group deviation if I do that, and then how the ratios changed. And what you see is animals that ratioed over 100 before now are below 100. And that's the foundation of those animals' EPDs. What I did is just bias their EPDs in an unfavorable way to me. Okay, I shot myself in the foot. I took bulls that were good and I made them look worse because I didn't spend the money to submit all the data. Okay? So you're not doing yourself any favor by selectively reporting data to a breed organization. You're making your animals look worse than they are. So a lot of organizations have what they call whole herd, or call it total herd reporting. A lot of them are forced on you, right? You got to do that or you pay more money. Others are voluntary. I think of Angus's Maternal Plus program kind of started out as a voluntary deal. And if you want reliable reproductive trait EPDs, think of heifer pregnancy, think of reproductive longevity, which most organizations call stayability or sustained cow fertility, total herd or whole herd reporting is a must, right? So that's the only way to get really reliable EPDs for those kinds of traits. And if you do that, right, if you're in an inventory-based system and you cull a female, it really helps to know why she left. And unfortunately, a lot of organizations have this long list of categories. You can tell them why she left, and then they have this catch-all called other. You know what the number one reason people get rid of cows is? Other, right? That's not particularly helpful. So say why she left, right? That's really helpful too. And what these systems do is help us delineate between those that failed, right, quote unquote failed because they just weren't given an opportunity, versus those that truly failed to conceive. If you think about a yearling group of heifers, some of those don't have a calf because we didn't expose them. And we've got to tell the system that, right? Those statistical equations can't magically figure that out. It only knows the data you submit, right? So we got to know that animals were actually there and exposed. Admittedly, data's messy sometimes, right? I've spent a career so far working with what we call field data, data that comes from breed organizations, and I can tell you it can get messy. And that's a concern both inside and outside of research settings. Even, I'll tell you, even in research settings, errors occur, right? And in industry, errors can be with and without forethought. That's a very kind way of saying, right, some people make mistakes on purpose. That happens because you're dealing with humans, right? Those errors, though, impact our genetic predictions, no doubt about it. And so being able to clean or categorize data based on quality can be really impactful for our genetic evaluation. Have any of you heard the saying, figures don't lie, but liars figure? Right? So sometimes I get hit with that in EPDs, right? They say, well, yeah, but the people submitting the data, right, they're cheating the system. And what I'm going to show you is we have some very sophisticated safeguards in place to ensure that doesn't happen. Which is related to this whole notion of machine learning, right? Artificial intelligence. You've heard about it before. Self-driving cars, maybe not the greatest example so far, because if you hear about self-driving cars, it's not about it working, okay? It's usually about a failure. But Netflix, if any of you watch Netflix, it recommends shows for you, right? That's machine learning. It took what you watched before and said, oh, I bet they'd like this one. Fraud protection, you ever get a call from your credit card company that said, hey, did you buy this? Right, that's machine learning because it learned about your spending patterns and then said, you know, the one for me was I apparently bought a bunch of overalls at a store in Maryland for large and tall men. That's a true story. And I was like, well, there's so many things wrong with that, you know, but they flagged that. We can use the same concept to flag data that just does not make sense. So here's an example of that. The top left pane are birth weights from contemporary groups that were measured with a digital scale. That's the gold standard for getting birth weights, digital scale. Top right is a hoof tape. Any of you familiar with that? Right? That's right, I'm not Big Brother here taking down names if you use a hoof tape or not. With a hoof tape, right, you measure circumference around the coronary band there, and based on that circumference, it makes a prediction of what that calf must have weighed. What you see there, though, is there's less variation if you use a hoof tape. It's a prediction, so it shrinks the amount of variation. Bottom right, real jagged, that's noisy. That's maybe like a digital scale, but wow, that's heavy, right? I'm just, 5-pound increments, close enough. And the bottom left is what I called fabricated, which suggests I know intent, right? I don't. But you'll notice shrunk variation, and it's what I call truncated. We never saw really big calves in those contemporary groups. So what we could use is a machine learning algorithm to classify contemporary groups of birth weight into which one of these groups they fall into, and then more appropriately weight those records in the calculation of EPD. And what that did was re-rank some bulls. So that 0.91 is the correlation in calving ease direct EPD. Before and after, we removed birth weight records that we called from fabricated groups. And the 0.86 correlation is between calving ease maternal EPD before and after. So those correlations are pretty high, but it impacts some breeders a lot if we're tossing out their records. And on tens of millions of animals in a breed association, that means bulls are going to shuffle around. And what we found out by doing that, the EPDs were actually more accurate. So again, the quality of data you turn in is important, and we do have safeguards against any of your colleagues that may not do it appropriately. The other part of messy data is sire misidentification. Dare talked about that, and you can see numbers 7 to 10% sire misidentification in sheep, 10 to 13% in cattle, 8 to 14% in goats. And that can really wreck a genetic evaluation if we have a lot of sire misidentification. And it's not only the sire, right? We have dam misidentification too. It happens, right? You have a snowstorm in our part of the world, cows and dams get shuffled up. We don't think it happens, but it does. And it breaks true kinship ties and then creates false ones. And that decreases heritability because we break the flow of genetic information through generations, and it leads to incorrect EPDs, which ultimately leads to incorrect selection decisions. Which, if you think about our foundational, the very first EPD we ever get, it's a pedigree estimate, half a mom, half a dad. And if one of those two is wrong, our pedigree estimate EPD is way off, right? Way off. Of course, their true progeny difference, true EPD, often, very often, is different than their pedigree estimate, and that's due to Mendelian sampling, that random shuffle of alleles from one generation to the next. But if we have sire or dam wrong, we start off in the wrong place. It's hard, right, to ever get back on track unless we correct that. You can imagine this bull. Anyone know what breed of bull that is? Cimbra. Yeah, it is. The Cimbra bull. We learn about sires through their offspring. So if this bull has 5 calves, and those values over there on the far right are how those calves deviated from the average of their contemporaries, that's how we learn about that bull as a sire. How are his calves performing against the calves of other bulls? And that really becomes the foundation of that bull's EPD. On average, right, what's the difference in his progeny, expected progeny difference? But if we incorrectly assign one of those calves to him, that messes up his EPD too, doesn't it? Especially when he's got a limited number of offspring. I also point out from this that offspring of one sire exhibit more than 3/4 the diversity of the entire population. It's a very fancy way of saying that, we have customers come to our sale and they want to increase uniformity in their calf crop. So they want to buy maybe half brothers. But those half brothers could be dramatically different in terms of their genetic potential for any trait. So what I tell them is, why not just buy bulls that have a similar EPD for the trait that you want to increase uniformity in? And maybe they're half brothers, maybe they're not. That's the better approach. The other thing I hear is, well, that good bull had a bad calf, or that bad bull had a good calf. Right, that happens. So if you look at these two bulls, one has an EPD of 40, the other has an EPD of 50. They're going to assort gametes that take on kind of this bell-shaped curve, right? A bull is going to pass on some good genetics to one calf, some bad genetics to another one. The EPDs are on average. Okay, over enough animals, our expectation is that 10-pound difference will hold. But it's not for every single calf. Really good question. So accuracy is not a measure of variability in the offspring. So a highly accurate bull can still have offspring that are variable. That whole variable of the offspring bit is really a function of how inbred is that bull. So you have a highly inbred bull that limits the different genetics he can pass on. You have a bull that's better, what I'd call heterozygous. He can now assort or pass on a lot of different variations of genetics. That impacts variability. Accuracy is really not a measure for that, though. The notion of accuracy really is how confident are we in that animal's EPD. The blue bell-shaped curve shows a high accuracy bull. We're confident his true EPD is pretty close to 40, right? The red bell-shaped curve shows a low accuracy bull. Still has an EPD of 40, but his true genetic value could be anywhere within that range. I'll show an example here in a second too. I think a more tangible way of thinking about accuracy is this notion of possible change. And so we can think about EPDs as kind of a mean, and then say, well, there's that EPD plus or minus something, right? Like a standard deviation. We call that a standard error prediction, okay? Our standard error of having predicted the genetic merit. So if I take an EPD plus or minus one of those standard errors, that says 68% of the time his true EPD falls within that range. Plus or minus 2 of those values says 95% of the time his true EPD falls in that range. And what I'll show you is when we genotype them, we increase accuracy and we narrow up those windows. So we become more confident of where his true genetic merit actually lies. This is an example. This is a possible change table from Simmental. Every breed association has a possible change table if you hunt hard enough on their website. And what it does is shows you the accuracy level and then different traits. So if I have a bull with an accuracy of 0.2 for the trait of calving ease, that's CE, that's the possible change value. That's the plus or minus value that you would add and subtract from his EPD. And this is an example. So just weaning weight. If I have a bull that has a weaning weight EPD of 40, his accuracy is 0.6, I could go to that table and find out the PC or possible change value is 4.6. So I could build this confidence interval between 35.4 and 44.6 and say, I'm 68% confident his true weaning weight EPD is in that window. I could go out and be 95% confident, and to be 95% confident, I expand that window and say, well, now I'm 95% sure his true genetic value for weaning weight's between 31 and 49. Where's this helpful? Think of a trait like calving ease. You have a customer that says, I want, they probably say need, but what they really mean is want, right? I want a bull that has a calving ease EPD of this. Thinking about it that way kind of helps, right? So how confident can I be his true genetic merit for calving ease falls within that customer's acceptable range? The other thing I wanted to point out relative to accuracy is the impact of turning out a group of bulls, right? So if I'm turning out a group of bulls, it's really not the accuracy of the individual bull's EPD that matters, it's the accuracy of the group. And so as I increase the number of bulls in a pasture, I'm dramatically increasing the accuracy of the average genetic merit of that group. And that's what this shows. So as I have more bulls, so more animals in the group, the error associated with that average dramatically goes down. In other words, the accuracy dramatically goes up. So you can think about turning out maybe 5 or so bulls. All of a sudden, even though they were all lowly accurate yearling bulls, I've got quite a bit of confidence in the average genetic merit of that group. Same thing could be said with pooling semen on bulls. Right? Dare hit on this, and I know Troy will talk about it more, but this gets to your question about the genomics bit, and I said we're doing a better job of assigning relationships among individuals. So as Dare talked about, the expectation of the relationship between you and one of your grandparents is a quarter. That range can be 0 to a half with no inbreeding. And I just met you guys, and we're going to assume that's a fair assumption. But if it's not, don't raise your hands, okay? This is actually real animal data. This is pigs, but the same thing happens in cattle. Red bars are expected value a quarter, but you can see using, in this case, it was about 50,000 DNA markers between individuals and their grandparents. The range in that relationship is about 0 to a half. A little more than a half in some cases because this was a nucleus swine farm, so they accumulate some inbreeding. So that very much happens. And so what that enables us to do then by genotyping is maybe you had a great-grandsire, right, that was really feed efficient. But that young bull you're trying to sell, if at the DNA level he's not related, right, to that really feed efficient bull, then the records from that really feed efficient bull aren't going to help the predictions of that yearling bull, right? That's the way it works. Tangibly, what are you doing by genotyping non-parent bulls? These are progeny equivalents, Angus, Hereford, and then IGS for various traits. The way you interpret this, and if we use birth weight just for examples here, AAA is Angus. So if I genotype a non-parent bull, that increases his accuracy to as if he'd already had 21 calves with a birth weight recorded. That's huge, okay? When you think about it that way, that's pretty big. That's before I ever exposed him to cows. Think about a trait like carcass marbling. You can make it as if he'd already had several offspring with a carcass measured before I ever exposed him to cows. Okay, so that's a pretty big deal. And by genotyping, what you're doing is allowing your customers more confidence in the product they're buying from you. That's the way I view it. Another way of thinking about that, picture of a Gelbvieh bull here. If we have this Gelbvieh bull that has a calving ease EPD of 9, yearling bull, so low accuracy of 0.2. If we assume the possible change value was 6.2, that says we're 68% confident his true EPD is between about 3 and 15 for calving ease. But if I genotyped him and boost his accuracy to 0.4 now, what I've done is narrowed up that window. So now I'm more confident, right, that his true EPD is perhaps within an acceptable range. So it begs the question, how are genomic EPD being used? I know when this technology first came to bear, right, there's a cost. That cost has gone down, though, believe me, over the past decade. There was the temptation to only genotype maybe the lead-off bulls in somebody's sale, right, the ones that had other breeder interest. Well, if you think about what you're doing, you've already decided not only which bulls are in the sale, but you already decided sale order, and you spent money on genotyping. There are no decisions to be made with that information. The only reason you pay for additional information is to enable a decision. So to do that, you genotype every calf born. Because what it should do is help you decide, well, which bulls am I actually going to sell? That's the way this technology is meant to be used. And it can be hard because that really good bull, as Dare said, you genotyping and all of a sudden he's not really good anymore. That's a tough pill to swallow. But the idea is which ones actually deserve to be sold. If you're just doing it for marketing, that's when you only genotype selected individuals. And that has a negative impact then on genetic evaluations because, as I said, we need genotypes coupled with phenotypes. So here's the seed stock responsibility. This is what we call the breeder's equation or the key equation. So the delta BV is the change in genetic merit per unit of time. So that's related to how much genetic progress or change I'm making. I'm hesitant to call it progress. It's change, right? And that's a function of this R is the accuracy of EPD. The little I is selection intensity. So intensity goes up, the more choosy we are about who's parents for the next generation. And then that sigma BB is related to the amount of genetic variation there is for the trait, and in the denominator L is generation interval. That's the average age of the parents when the next generation is born. In beef cattle, in seed stock settings, that's anywhere between 4 and 6 years, okay, generation interval. So to me, there's the potential for leaks, what I call leaks of genetic gain, if you look at this question, or this equation. So one is reduced accuracy due to lack of phenotypes and lack of genotypes. So if we're not collecting and recording phenotypic records, if we're not genotyping, that means we're not increasing accuracy. So that's a leak of genetic gain. Reduced selection intensity because we culled genetically superior animals for perceived flaws. Right? That happens, doesn't it? You've got that bull that their EPDs or indexes say, this is a really good one. You know, he's kind of heavy-headed or just doesn't look good, and so you cull him. That's a leak of genetic gain. Using older sires and not culling older dams. Okay, if you use old sires and you keep around old cows, that increases generation interval, which slows up genetic change. And that happens all the time, right? That really good bull that's decades old, you sample him. Well, that increased generation interval. The older cow thing, some of you, maybe all of you, are starting to get a little riled up about that, right? Because we all have that old cow that's really good. Think about what that means. If you have an old cow that's really good, that means that for years, you haven't made a heifer better. That doesn't bode well for what you've been doing, does it? Right? Ideally, on average, the young ones should be better than the average of the older ones. Should happen that way. Now, I'm not saying there's not some cow that just got a really good Mendelian sampling, right, and she's an outlier. But having your best cows genetically be your oldest cows says that your selection program hasn't been going very well for a while. Now, your commercial customers should want to keep older cows for depreciation cost, right? Cow depreciation costs can be huge. So they want to keep older cows. Seed stock producers, on the other hand, should want to turn generations faster to increase the rate of genetic change. Different between those two clientele groups. And you got to think like you're making genetics. Good question. So what if your genetic selection program is really dominated by traits you know impact your customer, right? Sustained cow fertility, those kinds of things. Well, we do have genetic predictions for that, EPDs. And so by selecting on that, you're increasing the genetic merit for it. And the idea then is your customers get the benefit from longer cows that last longer. We've got a unit manager at our seed stock herd, UNL, and man, he and I go rounds about that. But the other thing I submit to him, and I'd submit to you, is those running age cows in our seed stock herd, the cows that are 5 years old, 6 years old, they have considerable value to commercial producers, I'd argue. And so what we do is those cows that get to be 5 or 6, when they're still, prime of their life, I roll them out and I sell them as breds. In our system, I can do that to another research herd that's commercially focused, and they're tickled pink. Now they got a running age cow, right, in the prime of her productive life, calving problems gone, breed back problems gone, because we took care of that for them. So it kind of works out well in our system. So there's some value in being able to do that. Now, I'm not saying go home, cull all your old cows regardless of what their genetics are, right? I'm not telling you that. What I am saying is just keeping cows around longer because they're in the more productive period of their time, if they're not genetically superior, is really, really slowing up your ability to make genetic change. And then I mentioned here, not genotyping animals with records, particularly females. Oftentimes we think genotyping, that comes with a spin, so I'm going to genotype the bull calves because those are the ones I'm going to market. But if you go back and think about the progeny equivalent values I showed you, genotyping a heifer to come back into my seed stock herd has a lot of value. A lot of value, right? That may inform which ones I actually keep and which ones I send on down the road. And then I put, one of the first bullet points here, and my job as a seed stock vendor is to make decisions simple for your clientele and sell problem-free animals. Sounds really simple when you say it, right? But if you think about it, you're vendors. You want to sell an animal that, doesn't break a leg, right? Doesn't bang up the barn, those kinds of things, right? At UNL, I have never gotten a call that said, hey, that bull you sold us, his calves didn't grade well enough. Never gotten that call. The call I get, hey, we got him home and, he started tearing up the gates, right? You get those calls. Not often, right, but you get them. Now it's probably they took him home and, beat him when he was coming off the trailer or something like that. It doesn't matter. It's not their fault, my fault, okay? But you got to try to sell problem-free animals, and then I say make the decision simple for them. And by that, you never want to get to the point where you're putting together a sale catalog and you look at a bull and you say, well, man, he's not really good for a lot of these things. Let's just hope somebody that needs X finds this bull. What you've just said is he's got some problems, right? Our job is to make sure those bulls never get into the sale. And I always think of it, if somebody comes to our sale that doesn't know sick'em from come here about buying bulls, if they just close their eyes and throw a dart, they're going to go home with a bull that'll work for them, right? I've taken care of all the hard work for them. That's the idea. Well, now that I've told you, right, what your job is, so let's just see if it'll advance. Yeah, it just didn't like that slide. So I say here, and we talked about it before, phenotypes will always be king. So genetic evaluations will be best if there's a continuous flow of phenotypes. So I mentioned PAP, that's pulmonary arterial pressure, perhaps not as big a concern for you folks here, but certainly you send bulls to altitude, that's a concern, right? If people are raising cattle at altitude. So actually, PAP scoring cattle, feet and legs, so some genetic evaluations, some breed associations actually calculate EPDs for foot and leg score, and that's folks like you scoring them, right? Mature cow weight, which is crazy, but there's a dearth of mature cow weight records for a lot of breed associations, right? We need to actually weigh cows and body condition score them and turn those records into breed associations. Right? And nobody's sitting at a breed association saying, oh, Bob's cows are big, aren't they? Right? They're all big. But if we're going to allow producers a tool to change that, we need records. Carcass traits, that's a hard one, but if nothing else, the proxy through carcass ultrasound is useful. I'd say here the best way to tackle novel traits is to make them less novel. In other words, we got to collect phenotypes for them. And what's really important is quality phenotypes near selection candidates. So in other words, if several years ago I took some bulls to have feed intake data measured, and I did that several years ago, that had an impact on those bulls, and if I did heifers, perhaps on their offspring, but that impact dissipates over time as my animals become more distantly related to those animals that I put a heavy investment on in collecting information. This kind of illustrates that. In the green there, I have selection candidates. Think of your young bulls. I learn a lot by collecting data on them. I learn some from their parents. I learn very little from their grandparents. And I learn very, very little from their great-grandparents, right? Way to think about that. So my paternal grandfather played college football, and all of his brothers were college athletes. So based on them, you would think that, right, I should have been a college football player. Wow, would you have messed that up? Right? That's far enough ago that how they performed is not particularly useful to inform my prediction or the bulls that we're really wanting to predict. Here's an example of that. This is through simulated data, and what this former postdoc of mine did was built a simulation to carry out genetic selection for 15 generations. And what he asked was, well, in calculating the EPDs, what if I throw away, we called it truncated, threw away data, phenotypes, genotypes, pedigree, on animals that are 1 generation back from the animals we want to evaluate, or 2 generations back, or 3 generations back? Does that have an impact? And what you can see on the right panel is the animal's true breeding value, their true genetic merit after 15 generations of selection. And if I truncate data 1 generation back from the selection candidates, that has an impact. I'm losing information. But if I throw away data 2 to 3 generations back from them, it has no impact. I made the same amount of genetic progress. What that means is, as you think about making an investment in phenotyping and in genotyping, it needs to be a continuous investment. You can't just do it once and say, I'm good for a while. It has to be a continuous investment. So if I think about what you should do, that's bold, what you should do to help your customers, it's be an active participant. And being an active participant means you're collecting data and you're collecting reliable data because you need to be a steward of it. It starts with what you do on farm. The other thing, which is hard, is to be an advocate for change. Genomics changed genetic evaluations. It re-ranked animals. People don't like change, right? Especially in our industry. That bull was good. Leave his EPDs alone, right? But when there's change, when there's improvements, bulls are going to shuffle around. They should, right? If bulls didn't re-rank, why would we spend money genotyping them? You've got to be a student of genetics. I don't mean you got to go back to school and get an advanced degree, but your clientele view you as the experts in this field. And you don't want to get in a position where you're selling bulls to somebody that knows more about this than you do. That's a dangerous spot to be in, right? We've all bought vehicles before, which I hate that exercise. But it's really frustrating to talk to a salesperson and you think, I know more about this truck than you do, right? Just get out of my way, right? You don't want to be in that spot, which means you need to be a student of genetics. And understand critically, as Dare said, your profit is tied to your customer's profit. Sometimes we lose sight of that in the seed stock industry. I'm raising good genetics. Well, the idea is those good genetics should lead to increased profitability of my customers. That's what it should do. If they're not profitable, then I don't have a customer in the future. And continue to challenge us being academicians, at identifying emerging needs that you have as seed stock producers. Right? It's a partnership. Dare pointed out this very useful resource, sire selection manual. If you don't have one,
we have a copy for it.
Good. You got a parting gifts. And I'd just like to say thank you. ebeef.org, which Dare showed you. beef.unl.edu. Right, that's our UNL beef production website. Sorry if I offended the whole room by throwing that up there, but a fairly useful resource, we think. Beefimprovement.org, Beef Improvement Federation, which Dare and Troy and myself heavily involved with. And then the last is nbcec.org, has some very useful webinars recorded on there. So I don't know where we are with time, but I know I'm done.